Alright, today we look into the meaning of enthalpy. So we'll tackle some questions on this enthalpy. So first look at the definition of enthalpy. So enthalpy is an extensive property. So what again is extensive property? Extensive property means that the property can sum up its accumulative. For example, let's say we have a delta H1 and then we have another one, let's say delta H2. You can add up. So those property that can sum up, you call it an extensive properties. So enthalpy is used to quantify the heat flow into or out of the system in a process that occur at constant pressure. So to put it in very layman terms, so basically enthalpy means the heat flow. But this heat flow is occur at constant pressure. So if you look at the definition again, so enthalpy is equal to the sum of internal energy plus the product of pressure volume. So you translate into mathematical equations. So H equal to P plus delta H equal to E plus PV, and the pressure occurs at constant pressure. So therefore we don't have a delta P, so we only have P. So then we have delta H equal to delta E plus P delta V. As we learned previously, delta E is equal to Q plus W. And from W equal to minus P delta V, so P delta V will be equal to minus W. So from here we can get to the third stage here. So and after that we can actually cancel out the W. So overall we get heat. So this one show you that the delta H is actually equal to Q, which is the heat. So change of enthalpy of the system basically will be equal to the heat flow into or out of the system. So therefore we can have, if heat flow into the system, we call it heat gain. So in other words means endothermic reactions. So if the heat is flow out of the system, we have a heat loss, so we call it the exothermic reactions. So look at this two energy profile. So this one I call it energy profile. So on the left we have an endothermic, on the right we have an exothermic. So you can see that the endothermic graph, that the graph is going up, the exothermic, the graph is going down. So on the y-axis is not energy, but they label enthalpy, and in the middle you will see a delta H, and then the unit kilojoule per mole. Most importantly, if the graph is going up for endothermic, it will show you a plus sign. For the graph that's going down, exothermic, it will show you a negative sign. How do we get the plus and minus? Because according to the equation, delta H equal to the enthalpy level of the product minus enthalpy level of the reactants. So we take the product minus the reactant. In this case, the product is bigger value, so overall we'll get a plus. For the exothermic energy profile, you can see that the product is lower level compared to the reactant. So the product minus reactant will get a negative. All right. Okay, now look at this thermochemical equation. Is delta H negative or positive? So here indicate that the sign is a positive. So the delta H is positive. In other words, means that delta H is more than 0. So delta H more than 0 indicate this is an endothermic reaction. So endothermic reaction means that the system absorb heat from the surrounding. 6.01 kilojoules are absorbed for every 1 moles of ice that melts at 0 degrees Celsius and 1 atm. So you will see this 0 degrees Celsius and 1 atm always, because this one is referring to the standard conditions. So to translate into a thermochemical equations, so it sounds something like this. So ice H2O liquid, ice H2O solid, it will convert into H2O liquid. So the delta H is plus 6.01 kilojoule per mole. So take note that the kilojoule per mole, the per mole are referring to the H2O solid. Okay, we have another graph here. This one show you that the sign is negative, so that the delta H is a negative. Delta H is less than 0. So this one indicate is an exothermic reaction. So exothermic reaction means that the system releases heat to the surrounding. So example, we will have combustion. So for example, whenever you burn 1 mole of methane at 25 degrees Celsius and 1 atm, it will release 890.4 kilojoules of heat. So the per mole here once again are referring to the methanes. So next we'll go into more detail about thermochemical equations. So there are several rules you need to follow about this. So the first one, the stoichiometry's coefficients always refer to the numbers or mole of a substance. So look at this example here. So H2O solid melt to become H2O liquid. So the 1 in front and the 1 here are referring to the mole. Right. Point number 2. If you reverse the reaction, the sign of delta H changes. So for example, the first one is a solid change to liquid. The second equation, however, is basically the reverse of the first one, where your liquid convert back to solid. I want you to compare on the delta H. You can see that the value is the same, just that this one is in plus, this one is minus. So it means that whenever you gonna reverse the equations, or in other words means flip the equations, so you will change the sign of the delta H, but you don't change the magnitude of the delta H. So that's why both will still remain is 6.01 kilojoule per mole. Just that one become plus, the other one become minus. So for example, methane burn, we get CO2 and H2O. So you can see that this way the value is negative 890, but if you reverse it, the value is still the same, but it become a plus 890. Right, this rule is very important. Okay, rule number 3. If you multiply both sides of the equation by a factor n, then delta H must change by the same factor n as well. So if you multiply 2, the whole equation you times 2, the delta H you will times 2. So that's why it's no longer 6.01, but it becomes 12.0. And the sign remains. So this one, the sign will still become plus. So the magnitude will change. The sign remain. Alright. Last point. The physical state of all reactant and product must be specified in thermochemical equations. So here we have equation A and B. As you can see that the A basically referring to the melting process. So this one is a melting. Equation B are basically referring to the boiling process. So how do I know it's melting and boiling? Because there is a physical state. Solid change to liquid is melting. Liquid change to gas is boiling. Right? If you just write H2O becoming H2O, so how do I know is a boiling or is it a melting? Because as you can see in this example here, so the melting and the boiling, even though both are endothermic, but it shows you different value. You can see that the boiling absorb more heat than the melting. So this is very important that every student must indicate the physical state whenever you write a thermochemical equations. Alright. So look at this example here. Write the thermochemical equation with correct physical state and delta H and the energy profile for the following reactions. The melting of ice to become water absorbs 6.01 kilojoules of heat. So apparently they already give us the thermochemical equations. So once again, I want you to analyze these equations. So the kilojoule per mole here, the per mole here once again are referring to the solid ice. Alright. So next we'll proceed to drawing the energy profile because they asked for the energy profile. So the y-axis you label enthalpy because they give us here are all enthalpy value, the delta H. So enthalpy symbol will be H. So you can see that the sign is a plus. So the plus indicate that this one is an endothermic reactions. So endothermic reaction, the graph is going up. So you know that it's going up. So indicate, put the arrow going up. Here will become your reactant, here will become your product, but you label specifically what is your R and P. So the reactant here is H2O solid, the product here is H2O liquid. If you want to label the x-axis, you can. So here you can put the progress of reactions, and you can also put another, you can also say that this one is the reaction pathway, also can. But the x-axis definitely is not time, because we are not measuring rate of reactions. So take note, this graph is not complete because in the middle you have to indicate the delta H. So just copy whatever you have it here. So we get a plus 6.01 kilojoule per mole. All right. We have another questions here. Methanol, CH3OH, burned according to the equations. How much heat is given off when 75 grams of methanol is burned? So we are start with this information. First, we will find the mole of methanol, CH3OH. So to find mole, you take the mass, divide by the molar mass. So the molar mass of methanol, you have to calculate CH3OH, so 12.0 plus 1.01, you times 3 plus 16.0 plus 1.01. Alright, so use calculator, you get this is 32.04. So you divide, you get your answer 2.34 moles. And then we will make use of the thermochemical equation here. So especially this one, the sign is very important, is negative. So it means that 1 mole of the methanol that you burn, it will release negative 1454 kilojoule. How do I know this? Because I'm based on the thermochemical equations. Alright, another common mistake is that I almost forget. Whenever you calculate the molar mass, you no need to incorporate the coefficients. So this whole thing, you no need to times 2. Right, just stick to CH3OH. Okay, come back to the questions. So just now 75 grams you calculate is 2.34 moles. So we're using the ratio 2.34 moles of methanol. It will give us negative 3402 kilojoules of heat. So this will be answer lah. Right, next look at another example. How much heat is evolved when 266 gram of P4 burn in air? And then we have the thermochemical equation. So we start with the 266 gram. So first we find the mole of P4. So we have 266, take the mass, divide by molar mass. Phosphorus is 31, so you times 4. So it's 266 over 124. So calculate, we get 2.15 mole. Right here, we get 1 mark. And after that, we will make use of the thermochemical equation, especially this one. So it shows you that 1 moles of P4, it released negative 3013 kilojoules of heat. So therefore, 2.15 mole of P4, it will release negative 6478 kilojoules of heat. Right?